Welcome back to the deep dive. If you've been feeling the ground just constantly shifting under you every time a new AI acronym drops, LLM, RAD, token, agent, you are absolutely right to feel a little overwhelmed. Our mission today is to cut right through that noise. We're going to deliver a rapid but deep understanding of the core concepts that define modern AI.
Exactly. And we're not just here to define a list of terms. We're here to define the stakes. We are talking about a technology that is, radically reshaping how organizations work. Just think about some of the claims in our sources. Microsoft CEO Satya Nadella called AI the defining technology of our times.
And Sundar Pichai went even further. He said it'll have a greater impact than fire or electricity.
It's a massive claim, but you can already see it happening.
Absolutely. Look at someone like Jeff Bezos, who credited Amazon's huge leaps in logistics and pricing directly to their AI processes. This is really the difference between staying current and, frankly, being left behind.
So to give you that roadmap, we've structured this deep dive into four critical parts. We'll start with the core brain, the foundational models. Then we'll tackle customization. How do you teach that brain your specialized knowledge? After that, we'll look at the AI senses, so images, video, and then finally we'll get into what might be the biggest thing of all, AI agents. These are models designed not just to talk, but to act.
Okay, let's jump right in with the foundation. We hear this term new AI, which seems to have exploded around 2023. So what exactly is a foundational model? How is it different from the old AI we used to talk about?
The term foundational model is really the key here. Think of it as the base engine. Unlike older AIs that were built for one very narrow task, these are massive generalized models. They're trained on, huge swaths of the internet, and they can perform a vast range of tasks, often with zero specific instruction. An LLM, a large language model, is just the most famous type, the one built for language.
Right, so the LLM is the big generalist, the one that can talk about almost anything because it's basically read the whole internet. But now we're seeing the rise of SLMs, small language models. If bigger is usually better in tech, why would anyone go for a smaller version?
That's a critical trade-off, and the sources really emphasize this. Size is all about efficiency. An LLM gives you, yes, the highest competence for really complex, abstract problems. But an SLM is a specialist. So if you have a very specific, narrow task, say classifying thousands of support tickets, an SLM is faster, it's cheaper to run, and crucially, it has lower inference latency.
So using a huge LLM for a simple task is just overkill.
Complete overkill. You're just burning resources for no reason.
Okay, that brings us to the mechanics. It's so easy to think of these things as magic, but they're really just incredibly sophisticated prediction machines. How do they actually work?
Well, at its absolute core, an LLM is playing this incredibly complex game of predict the next word. When you give it a prompt, it's just calculating the probability of what word or sequence of words should come next. To do that, it first has to break your language down into its basic unit, and we call that unit a token.
So if the token is the Lego brick of AI language, a word, maybe part of a word, some punctuation, what's the limit? How many of those bricks can the AI hold in its head at one time?
That limit is called the context window. Just think of it as the AI's short-term memory. It defines how much information your prompt and the conversation so far, the model can look at all at once to figure out its next move.
A bigger context window sounds like it would always be better, right? But the sources talk about a cost of context. If you have more memory, why wouldn't that just be the best solution?
Because that memory comes with a lot of computational baggage. Processing all those tokens at the same time massively increases the cost and, more importantly, the latency, the response time. Every time you double the context window, the time it takes the model to think can often increase exponentially.
So for a business that needs an answer in milliseconds, you have to trade some of that deep context for speed. It's an architectural decision.
It's a crucial one.
Okay, so once we get the components, we need to control the output. That starts with prompt engineering, which, as the sources keep reminding us, is not magic.
It's not magic at all. It's just about giving clear, well-structured instructions. The model is literal. The better your input defining a role constrains the format you want, the better and more predictable your output will be. And the second major control lever is temperature.
Right, the creativity versus precision knob. What's actually happening under the hood when we turn that dial?
You're adjusting the math, the probabilities of word selection. When you set the temperature very low, close to zero, the model just sticks to the highest probability path. It becomes very deterministic, very factual. But if you turn it up, you're telling the model to explore some of the lower probability options, and that introduces novelty, creativity, a bit of randomness.
Which leads us straight to the most famous error state,
Yeah.
the hallucination. That moment when the AI confidently states something that's plausible, but completely false. We all know it's a bug when we need facts, but one source had a really compelling argument that it can also be seen as a feature. How is that possible?
It's all about your intent. If you're using the model to, say, summarize a legal document, a hallucination is a critical show-stopping bug.
Hmm.
But if you're using it for creative writing, for brainstorming new ideas, for fiction, that ability to move beyond verifiable data and synthesize novel, unexpected connections, well, that's the core value.
It's the difference between needing verifiable truth versus needing novelty.
Exactly. A higher temperature gives you a better chance of both valuable creativity and costly hallucinations.
And to help manage all this, we have transparency tools. Can you tell us about the model card and the benchmark?
The model card is essential. It's like the nutrition label for an AI. It tells you about its training data, its known limitations, any potential biases. You absolutely need to read it. Then you have the benchmark, which is like the SAT score for an AI. It's a standardized test that lets you objectively compare how one model performs against others on common tasks like reasoning or coding.
Okay, so that sets up the brain. The next big challenge, our module 2, is customization. The base model is never enough for a specific business, so the number one question is always, how do we make it know our stuff?
And for that, we have two dominant methods: retrieval augmented generation, or RAG, and fine-tuning. Let's start with RAG.
RAG, that's the one with the open book test analogy. The model gets to look things up before it answers.
Precisely. The process is pretty straightforward. A query comes in. But before the LLM answers, the RG system first emisent retrieves relevant documents from an external source, your company's internal wiki, a database. It then augments your original prompt with that retrieved information, and only then does the LLM generate the final answer, and it can usually even cite its sources.
That sounds amazing for accuracy and for having the freshest data, but doesn't that extra lookup step add a delay? Are we trading accuracy for that inference latency again?
That is the primary constraint. Yes, you're adding an extra mandatory step. While the retrieval itself is incredibly fast, you're still adding that search and augment step into the process. So for a mission-critical, low-latency use case, RG might introduce too much of a delay. It's a design choice you have to make.
So what's the tech that powers that super fast external search?
That would be the vector database, which you can think of as the external brain for RAG. To find the meaning of your query quickly, RAG uses something called embeddings. Embeddings are just numerical representations vectors that capture the semantic meaning of a piece of text. The vector database stores your documents as these vectors, so it can instantly match your query to the most relevant documents.
And a huge benefit here, especially for compliance and security, is data privacy.
RAG is fantastic for privacy. Your proprietary data stays locked in that secure external vector database. You're not actually changing the foundational model itself, you're just giving it some temporary context. Your confidential data stays safe and separate.
Okay, now let's contrast that with fine-tuning. If RAG is the open book test, fine-tuning is grad school.
That's a great way to put it. Fine-tuning is about teaching the model a permanent new skill or a new style. You take the massive pre-trained model, that initial training is called pre-training, and then you continue training it on a smaller, very specific data set. You're literally changing the model's internal weights to specialize its behavior.
But if that knowledge is now a permanent part of the model, what's the privacy risk there?
You run into what's called data contamination risk. Because you're permanently changing the model, that specific knowledge you fed it could potentially be recalled or leaked in unexpected ways down the line. So your security has to be much, much tighter. It's really best for teaching a style like your brand's voice, rather than teaching sensitive facts.
And training these models is famously expensive. That's where PEFT comes in, right? For efficiency.
Right. PEFT, or parameter efficient fine-tuning, is the solution to the cost problem. Traditional fine-tuning means retraining billions of parameters. But PEFT is revolutionary because it only tweaks a tiny fraction of the model's weights. It lets developers get almost the same result with far less time, money, and power. It's like changing the fixtures instead of remodeling the whole house.
So the big decision. RAG versus fine-tuning. For someone trying to talk to their dev team, what's the simple way to frame that choice?
It boils down to the type of problem you're solving. Choose RAG if you have a knowledge problem. You need up-to-date facts. You need citations. You need real-time data. Choose fine-tuning if you have a skill problem. You need a new tone, a new format, or a very specific style.
And the best advice from the sources, don't just pick one.
You can, and often should, use both. fine-tune the model to learn your company's voice, then use RAG to give it real-time, verifiable knowledge.
Okay, that covers text and customization. Let's move to section 3, the AI's senses generative AI beyond just language. Visuals, audio.
We're talking about multimodal AI, an AI that can see, hear, and talk, processing different types of data at the same time. The most striking example lately has been models like ChatGPT 4o combining vision and language.
Which moves AI from being just a text box to an active collaborator. What's a real-world use case for that?
Oh, think about customer support. Instead of trying to describe some technical glitch in a chat, a user can just upload a screenshot or a quick video of the error. The multimodal AI sees the error message, it sees where the button is, and it understands the user's text. You get to a solution much, much faster.
Now, what about pure creation? The incredible images from tools like Midjourney or DALL-E. The technology behind that is the diffusion model. How does that actually work?
A diffusion model works like a sculptor, but in reverse. It starts with a canvas of pure, random noise, just static. Then, guided by your text prompt, it goes through a series of steps to gradually denoise that image, refining the pixels until a coherent picture emerges from the chaos.
So it's not pulling from a database of images, it's learning how to reverse the process of an image turning into noise. Now, we used to hear a lot about Jen's generative adversarial networks for making fakes. What's the main difference?
Jans used two competing networks, a generator making a fake and a discriminator trying to spot it. It was this constant battle. Diffusion models generally produce higher quality, more coherent images, and crucially, they are much easier and more stable to train than Jans ever were.
And this is all expanding into video with models like Sora and even voice cloning and music.
The capabilities are advancing way faster than the legal frameworks can keep up, and that immediately brings up the critical ethical question our sources highlight. Who owns AI-generated art? Is it the person who wrote the prompt, the company that built the model, the artist whose work was in the training data? That debate is reshaping creative industries right now.
That sets us up perfectly for Section 4, the revolution of action, AI agents. This feels like the shift from an intelligent partner to an eponymous workforce.
Exactly. This is the next big thing. The key distinction is that an AI agent is designed for doing, while a chatbot is designed for talking. An agent is like an autopilot for complex, multi-step tasks that have to cross different apps and systems.
And for an agent to actually do something, it needs a way to think. How do they work through a problem?
They often use a framework like REACT, that's reason plus act, so the agent doesn't just respond, it follows a loop. First, it reasons about the task. Then, it decides on an action like calling an external tool. Then it observes the results and reasons again to figure out the next step.
Okay, let's use the flight booking example. If I tell an agent, book me the cheapest non-stop flight to Denver next week, how does it use React and tool use to do that?
Well, the first reasoning step is to identify your constraints. Denver, next week, cheapest, nonstop. The first action is to call the flight search tool, which is just an API. The observation is the list of flights that comes back. The next reasoning step is to filter that list for cheapest and nonstop. And the final action is to call the booking tool to actually reserve the ticket. It moves through the steps logically and on its own.
For that to work, the agent needs to talk to thousands of different apps, travel APIs, calendar APIs, you name it. Every app has its own API, its own menu, but they're all formatted differently. That's a huge translation problem, which brings us to the Model Context Protocol, MCP.
The sources are pointing to MCP as the critical enabling technology here. Think of it as the universal translator for all APIs. Instead of developers having to code how an agent talks to every single different API, MCP provides an open standard language. This means any agent using MCP can use any tool that also uses MCP. It turns a bunch of isolated tools into a single, unified ecosystem.
And just to clarify, how is this different from a RAG?
A RAG is about fetching information to help with a conversation. MCP is about enabling the agent to take action using an external app. So RID is for knowledge. MCP is for doing things.
This autonomous capability is really what's driving the idea of an AI-native future, where your phone isn't just a collection of apps, it's an agent.
It's the ultimate evolution, right? Your phone becomes an intelligent agent that manages your life. But this also brings us to the core risk. When you let systems take autonomous actions, the potential for errors, for bias, for unexpected consequences, it all scales up dramatically. The governance and safety of agents is a huge area of research right now.
So to make all this actionable for you listening, let's pivot in our last section to the business technical bridge. Understanding this jargon gives you a massive edge when talking to dev teams.
This translation skill is absolutely crucial for your career. Let's run through two quick examples.
Okay, so you go to your dev team and say, I need our chatbot to know all the specs of our new product line by tomorrow.
The technical translation of that need is, do we need to quickly index the new specs and update the vector database for our R-GUI system? You're immediately pointing them to the right architecture R for fast new facts instead of asking for a huge, slow retraining.
Or if the need is about branding, I want our chatbot to have a very consistent formal tone that perfectly matches our brand guide.
The technical question becomes, is this a persistent style issue that requires us to fine-tune for tone, or can we get there with better prompt engineering?
Yeah.
You're showing you understand the difference between a temporary instruction and a permanent change.
Let's also demystify the speed jargon. When you ask, why is the AI so slow? What are the key terms you need to know?
You're really asking about inference latency. That's the time it takes the model to give you an answer after it's been trained. And a potential solution a developer might mention is quantization.
And what is quantization in simple terms?
It's a process to make an AI smaller and faster.
Yeah.
You're basically reducing the precision of the numbers the AI uses for its calculations. This lets the model run on less powerful hardware and speeds things up dramatically, sometimes with a tiny trade-off in accuracy. So your informed question becomes, what's our current inference latency, and could we deploy a quantized version of the model to reduce it?
That vocabulary just completely changes your role in the conversation from a passive consumer to an active leader.
And that's the whole point. Knowledge is only valuable when you can apply it.
So we've covered the core of the LLM brain, its tokens, its memory, and how we customize it using ARGI for accuracy and fine-tuning for style. And we've looked ahead to the incredible future of AI agents that don't just talk, they act.
The core concepts are now in your toolkit. But here's the final thought to take with you. Start thinking in agents. Try to reimagine your entire product or your workflow, not as a series of separate tasks, but as a potential agentic workflow. How would you design a factory line of AIs, each with a special role, all working together to achieve a huge goal? That's where the truly disruptive transformation begins.
Use these concepts to light up your tech journey and gain a commanding edge in every technical conversation you have from now on. That's all the time we have for this deep dive. Until next time, stay curious.